universe was born from a Big Bang nearly 14 billion years ago. But was that really the beginning of time? Two theorems are often used to argue that it was: the Penrose-Hawking singularity theorem and the Guth-Vilenkin theorem. In 2023, we traveled to the Perimeter Institute of Theoretical Physics to meet some of the scientists who have recently re-examined these theorems and come to a surprising conclusion.
My interpretation of the Penrose-Hawking theorems is simply that when we get sufficiently at sufficiently high densities, energy densities, we need to change our model, and it is very well possible that there will be no singularity and that time has no beginning. It is also possible that time is emergent, that our basic model of nature has no space and has no time, and that space and time are emergent concepts, in which case there would be no singularity either. So it is definitely not true that the Penrose-Hawking theorems prove that there was a Big Bang singularity.
One important distinction to make is between a singularity, where the curvature of space-time becomes infinite, and geodesic incompleteness. But what is a geodesic?
A geodesic is essentially the path that an observer would follow in space-time, but just following the curvature of space-time.
What does it mean now for these geodesics, these highways, to be incomplete? It just means they have dead ends. It could be in time or it could be in space. If it's in time, it means the observer who is moving on these, free-falling in these places, could in future their time end, so their clocks stop working.
You could have a space-time that is geodesically incomplete, but which nevertheless does not necessarily have a curvature singularity. That being said, are more common examples of singularities like the singularity at the center of a black hole, or that of a putative Big Bang cosmological singularity. Those would be examples where we have both geodesic incompleteness and an actual curvature singularity, an actual blow-up of the space-time curvature at that point.
See, when I wrote my first paper, the 1965 paper, as it came out, I think singularities were in the title. But in the arguments, I think it was more that I said something's got to go wrong. It could be negative energies, it could be quantum effects show that space-time doesn't become a continuum, or it could be this or that or the other thing, incompleteness, or maybe we don't have a Cauchy surface, and things like that. And I didn't say this proves there's a singularity. I was always nervous about using the term singularity because I wasn't quite sure how to define it. Does it mean that the curvatures become infinite? What does it mean? Does it mean inextendable in any sense of the word? And since there was that vagueness about it, I tend not to use it. But on the other hand, Stephen was absolutely brash about using the word singularity, and he thought these theorems showed there was a singularity. And if you meant incompleteness in some sense, that was a singularity. So he had a broader notion of what the term singularity actually meant. I was more cautious about it, certainly in my initial papers, but when Stephen and when we wrote together and all that, I began to adopt his terminology, mainly because he was using it all the time, and okay.
And Stephen was often saying, this proves the universe, if we've got a proof now the universe had a beginning. Was that your view then? I know it's not your view now.
So much.
The Penrose-Hawking theorem that supposedly proved a beginning of time assumed that gravity is always attractive. But we can solve a number of problems with standard cosmology by introducing a period of repulsive gravity known as inflation that violates this assumption and is thought to lead to a multiverse which exists eternally into the future.
I was working with Arvind Borda and Alex Vilenkin to understand what we can learn about how inflation might have started and how far back it could have gone. And in particular, once we realized that inflation could be eternal into the future, it seemed like a very natural question to ask, could inflation have also been eternal into the past? And what we found was that inflation could not be eternal into the past. What we basically managed to achieve was proving a theorem which says that any expanding region of space-time that has some minimum expansion rate can only go back so far and not infinitely far. So that means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever up until the present time.
The theorem proves that inflation must have a beginning, right? The universe as a whole, the theorem doesn't say that. It says that the expansion of the universe must have a beginning.
The theorem says the universe could have not always been expanding. So whether that means there was a beginning, so then beginning out of something else, some other physics maybe, or maybe beginning from a different phase of the universe, which maybe was contracting, maybe it was static. So then we can explore all of these possibilities. I wouldn't a priori rule out any of them.
Until the 1960s, scientists believed that a black hole had a singularity at its horizon rather than just at its center. But it was then shown that was an illusion generated by a poor choice of coordinates. The new work published earlier this year considered whether the Big Bang singularity might be the same.
We looked at the very question of, let's say inflation is always happening to the past, and we have spacetime that appears to be geodesically incomplete, very much according to the Guth-Vilenkin result. Then is the past boundary of that spacetime just an artifact of the coordinates, and can we extend it beyond that boundary into another phase of the universe, or is it really inextendable and singular, perhaps in the sense of a curvature singularity? We found various conditions for how the universe could approach that past boundary in just the right way for it to be extendable into another phase of the universe.
One scenario that has been found that can go beyond the boundary to the past set by the BGV theorem is the so-called de Sitter spacetime, which is a hypothetical universe that has no matter but a cosmological constant that causes space to forever expand.
De Sitter spacetime is one in which the rate of expansion is accelerating. So it is the prototypical inflationary spacetime. Now, we cannot live in exact de Sitter because it's an idealized solution, and we know we have matter fields in our universe, not just a cosmological constant. And so when we talk about the very early universe and inflation, we talk about quasi-de Sitter spacetimes that are not quite de Sitter, but presumably very close to de Sitter. And then the question is, okay, they could appear to be geodesically incomplete, those quasi-de Sitter spacetimes, but is that an artifact of the coordinates? Can we extend the spacetime beyond the apparent past boundary, or can we not? And the Guth-Vilenkin theorem does not answer that question.
We decided to also look into this more realistic inflationary scenarios where you're not exactly de Sitter, and then see, does the same thing happen? Are there ways for the observers to go beyond the boundary of where the theorem says things should stop? And then more specifically, we looked at the geometry itself, so geometrical structure. And we see that, well, under certain conditions, if this inflationary, so we classify them and say, well, these are the inflationary scenario, they could fall here, there, and different classes. Some of them, yes, things can go very wrong, but there are some of them that geometrically nothing dramatic happens. You can extend them beyond that boundary. They enter a different phase. What the physics there is, and is it realizable, we haven't figured it out yet, but you can do it.
We found that in the context of the Guth-Vilenkin theorem, situations where light rays would appear to end on a boundary can actually be extended beyond that boundary if certain special conditions are respected. Now, whether these conditions are realistic or not is still an open question and involves revisiting the physics that is relevant to this regime of the universe, and that's still an open question.
So we basically classify these different scenarios of inflationary background expansions, and we say, well, some of them, yes, things can go wrong, and for example, you get singularities. Some of them, we can find that you can go beyond the boundaries, and we show how mathematically you can go beyond that past boundary of expansion. In fact, some of our solution it looks like they're going into static universes. Some of them seem to be going into contracting universes.
I wrote this paper with my student, Joe Lesnevsky and Paul Davies, where we highlighted that there is an ambiguity in the way that one defines the average expansion rate of the universe in the BGV theorem. And depending on how one defines this, one can get different answers. And because of this, we found that it is in fact possible to find solutions which in general are inflating eternally into the past and into the future. This is a controversial point somewhat, but mathematicians would say that they used an inappropriate definition for geodesic completeness. The problem is with the BGV theorem, it depends on how you compute the average expansion rate, right? It depends on the limits that we take. And if you take the limit to be from the infinite past to a certain point, then you get one answer. But if you take the entire limit of this from minus infinity to plus infinity, then one gets a different answer for the expansion rate.
I believe if we insist on inflation being really happening all the way as far as we can into the past, then I am tempted to believe that there was really a singularity, because one would need very special conditions for that space-time to actually be extendable and exist forever, and for geodesics to be really complete. The possibility is there. We derive the conditions, but is this physically realistic? The question is still open. Then, if we drop the assumption that inflation was really eternal as far as we could into the past, I think many things can happen, and many examples in which the universe did not have a beginning. Or if we just look for alternatives to inflation itself, then most of the theories that our people come up with are ones in which there was no singularity whatsoever, and where the universe existed forever. Whether that be a cyclic universe, a loitering emergent universe, a bouncing universe.
The idea that the BGV can be violated by either a static or a bouncing universe was already known before the new paper. So what's different in this new work?
What was different was we found exact or more rigorous geometrical structure to show that nothing drastically necessarily happens at the point. So the interpretation, some were saying, well, it means something like a singularity is happening, something bad is happening at the boundary. And we are saying, well, geometrically, not necessarily. Yes, some cases, something drastically happening, but there are also these other cases that geodesics can be completed and can go beyond the boundary.
A prior contraction can violate the condition of the BGV theorem that the universe on average is expanding. But how viable is this scenario?
There may be problems with contracting universes because basically contracting universes are highly unstable. If you have, for example, the galaxies are formed by gravitational instability. You have small overdensity and attracts matter and it grows. In flat space, it grows faster than an expanding universe. When the universe expands, it slows down all these instabilities. But in contracting universe, it grows catastrophically. So if you have some inhomogeneities in this contracting universe, they would grow out of hand. For example, if you have bubble forming, all these bubbles, instead of being driven away from one another, they will be driven towards one another. And so the whole thing will fill up with bubbles and inflation will end.
to me, it's pretty obvious that if you want to get a bouncing scenario that works, you have to go beyond the realms of general relativity. But that is what we are doing. In fact, I have my favorite theory of modified gravity, which I think it works. Yes, it is not the simplest theory of gravity that we know and love, and it's not Einstein's theory of gravity. But I think more or less all of us know the limitation there, and we have to and it's not a theory, so there's, we know we have to go beyond general relativity. At what level and to what extent? That's the question that everybody's wondering. People do quantum gravity. They're doing a very top-down approach to this question.
Now, some people have claimed that a bouncing cosmology is unstable and that we will never get a nice expanding universe if we start in a contracting universe. Now, a lot of these analyses are again obtained using Einstein gravity, and we have to go beyond Einstein gravity. And now there are concrete models where you can get a bouncing universe with fairly mild changes to the physics.
One possibility for going beyond Einstein is a quantum theory of gravity, like loops or strings. Another option is what are known as modified gravity theories, where slight tweaks are made to Einstein's equations. One example of this is known as Kuskouton gravity.
So I'm working on this modified gravity, the version that me and collaborator came up with about a decade ago, I believe, where it's very minimal adjustment to general relativity in some sense, because we don't add any new engines to the theory, if you would say, something new matter component or anything. It just very minimally tweaks the equations without any drastic implications. In fact, the reason I call it Kuskouton, because if anybody that has done gardening, there are these plants that go around other plants, but they don't have any roots. They just follow other things. So they do have some impact, but they're not like at each new weeds or anything in your garden that can grow on them by themselves. So Kuskouta is the Latin name for those plants. So I named the theory Kuskouton because it's kind of like that. It's kind of like a parasite that modifies things slightly, but it doesn't just grow out of nothing. And this theory seems to achieve exactly what a bouncing scenario would require to go from contraction into expansion, which basically, with this slight adjustment, it makes the background space-time bounce off without this other component, if they were there, would run. So that was the usual problem in the old way, why the bouncing scenario were problematic, because you had these additional things running around and then at the bounce they would blow up. But now you don't have them, so therefore you get the background space-time to bounce off without anything else going wrong.
Within the context of Einstein gravity, it's actually impossible to get a cosmological bounce without violating certain energy conditions. In other words, having some unusual form of matter involved. We say the null energy condition. But what we have done now is we have considered some other theories outside of Einstein gravity. Theories in Einstein's gravity, part of the reason for this is Einstein's gravity, the way it works out, which is quite beautiful, is on the left-hand side of the equation, we have the curvature of space and time. On the right-hand side of the equation, we have the energy density of matter. Even at the most fundamental level of the equations, right, from an action principle that you can separate matter from curvature in a direct way. But there are ways that we have found that you can braid together the space-time, the gravity, with the matter content, and it becomes much less trivial, right, to disentangle the two from one another. And within these models, using this kind of matter, which we call it, it's a Galilean matter, we call it, it is in fact possible to get a bounce, to violate the null energy condition, which is the necessary criteria to get a bounce in the first place, and to do it in a way that's stable without the typical problems that one can encounter in a contracting universe.
There's also a scenario which we call the emergent universe scenario. And there, the idea is that there's the physics that describes matter and gravity at the quantum level that might lead to a state which has no usual space-time interpretation. It's a quantum mechanical state, and then out of that state we might obtain an expanding universe. And in 1989, Guth and myself, we had a toy model of this called string gas cosmology, where we started from basic ideas of string theory, ideas that differentiate point particle theories from string theories. And recently we've developed or postulated an implementation of that which starts from deeper concepts of superstring theory. This is a so-called matrix model, and out of this matrix model we obtain space and time. And this matrix model, it's a matrix model in a finite temperature state. And in a finite temperature state you have thermal fluctuations, like you have fluctuations in a hot gas. And then we showed how these fluctuations can give rise to the inhomogeneities and anisotropies which are observed in the universe. So the emergent scenario is a third scenario for the evolution of the universe. So there's the standard Big Bang scenario where the universe starts in a singularity. There's a bouncing scenario, and there's the emergent scenario.
Border, Guth, and Vilenkin suggests that inflation cannot be past eternal, so it must have had a beginning. At least that's the way that they portray it. But what really it is about is there's a trajectory of a particle, if you look at it, and it goes back into the past, and what this particle experiences. Now, the question is, does that actually tell us anything about the universe as we know it? Now, particles, as we know, don't actually make up the universe now. So the universe, the quantum universe, is not made out of particles, they're made out of fields. So particles are only an approximation in certain limit. And especially when you go to early times, when things become more quantum, the notion of particle becomes less and less defined. But what does it tell us about our universe? If our universe is not made out of particles, but made out of quantum fields, and it's not necessarily classical geometry, but a quantum geometry. So these are all assumptions that we know are going to break down at early times, and we know fundamentally cannot be correct in a quantum theory of gravity or quantum theory of a space-time.
It could be that the whole concept of a continuum space-time completely breaks down. Perhaps the concept of time and even of space, we lose it. And if we lose it, then maybe the question of was there a beginning, maybe that question is nonsensical in the first place.